For millennia, humans have pondered the composition of our universe. What are the fundamental building blocks of everything we see and touch? The answer lies in the infinitesimally small world of atoms. Atoms are the smallest unit of an element, like tiny, indivisible spheres that make up everything around us. Imagine a world made entirely of Lego bricks. Each brick represents an atom, and just like Legos can be combined to build complex structures, atoms join together to form molecules, the building blocks of matter. But what lies within these tiny, fundamental units of matter? For centuries, the atom was thought to be the smallest possible particle. However, at the dawn of the 20th century, groundbreaking experiments revealed a hidden world within the atom itself. This is the story of how scientists peered into the heart of matter and unveiled the secrets of the atom's core, the nucleus, and the particles that reside within it, the proton and the neutron. In 1911, Ernest Rutherford, a physicist from New Zealand, conducted an experiment that would revolutionize our understanding of the atom. He fired tiny, positively charged particles called alpha particles at a thin sheet of gold foil. Based on the prevailing model of the atom, Rutherford expected the alpha particles to pass straight through the gold foil with little to no deflection. After all, the atom was thought to be a diffuse cloud of positive charge with tiny electrons scattered throughout. However, the results of the experiment were astonishing. While most of the alpha particles did pass through the foil with minimal scattering, a small fraction were deflected at large angles. Some even bounced directly back towards the source. "It was quite the most incredible event that has ever happened to me in my life," Rutherford remarked. "It was almost as incredible as if you fired a 15-inch shell at a piece of tissue paper and it came back and hit you." Rutherford's gold foil experiment led to a profound realization. The atom was not a diffuse cloud, but rather mostly empty space with a tiny, dense and positively charged core. He called this core the nucleus. But what exactly was the nucleus made of? Rutherford continued his experiments, this time firing alpha particles at nitrogen gas. He observed that the collisions produced particles with the properties of hydrogen nuclei. Rutherford concluded that these hydrogen nuclei, which he called protons, were fundamental particles within the nucleus of the atom. The proton carried a positive charge equal in magnitude to the negative charge of an electron, but with a much greater mass. The discovery of the proton was a major breakthrough. It provided the first glimpse into the structure of the atom's nucleus and hinted at the existence of other yet unknown particles residing within. While the discovery of the proton was a major leap forward, it also presented a new mystery. The mass of an atom's nucleus was known to be greater than the combined mass of its protons. What accounted for this missing mass? In 1930, German physicists Walter Botha and Herbert Becker bombarded beryllium with alpha particles. They observed a strange, highly penetrating radiation that they initially believed to be high-energy gamma rays, a form of electromagnetic radiation. However, this mysterious radiation behaved differently than gamma rays. It was far more penetrating and interacted with matter in unusual ways. The scientific community was baffled. What was this strange radiation emanating from the beryllium? The answer to this puzzle would come from further investigations, leading to the discovery of a new fundamental particle, one that had been hiding in plain sight. 2 years later, in 1932, Frederick and Irene Joliot-Curie, a husband and wife team of physicists, conducted their own experiments with the mysterious radiation emitted by beryllium. They made a crucial observation. When this radiation struck paraffin wax, which is rich in protons, it ejected protons from the wax with high energy. This observation was perplexing. If the radiation were indeed gamma rays, as Botha and Becker had proposed, it should have interacted very weakly with the protons in the paraffin. Something else was at play. The Joliot-Curie's experiment provided a crucial clue that paved the way for the discovery of the neutron. They had unknowingly produced neutrons in their experiments and observed their interaction with matter, although they did not identify the neutron itself. In 1932, the same year as the Joliot-Curie's pivotal experiment, British physicist James Chadwick repeated their work, but with a different goal in mind: to definitively determine the nature of the mysterious radiation. Chadwick meticulously analyzed the energy and momentum of the particles ejected from paraffin and other materials when bombarded with the beryllium radiation. His calculations led him to an astonishing conclusion. The radiation was not composed of gamma rays, but rather of neutral particles with a mass very close to that of the proton. Chadwick had discovered the neutron, the missing piece of the atomic puzzle. The neutron, a neutral particle residing in the atom's nucleus alongside the proton, accounted for the missing mass that had puzzled scientists for years. The discovery of the neutron completed our basic understanding of the atom's structure, a tiny, dense nucleus composed of protons and neutrons, orbited by electrons. The discovery of the neutron revolutionized our understanding of the atom and opened up new frontiers in nuclear physics. Scientists now knew that the atom was not the fundamental, indivisible particle once imagined, but rather a complex system with its own internal structure. The nucleus, once a mysterious entity, was now understood to be composed of protons and neutrons, collectively called nucleons. The number of protons, known as the atomic number, determined the element to which an atom belonged. The total number of protons and neutrons determined the atom's mass. This new understanding of atomic structure laid the foundation for countless scientific advancements, from nuclear energy to modern medicine. The discoveries of the proton and neutron were not merely abstract scientific achievements, they had profound implications for our understanding of the universe and our place within it. These discoveries gave birth to the field of nuclear physics, leading to advancements in nuclear energy, medicine, and our understanding of the cosmos. The processes that occur within the nuclei of atoms, governed by the interactions of protons and neutrons, power the stars, including our own sun. From the smartphones in our pockets to the medical imaging technologies that diagnose and treat diseases, the legacy of the proton and neutron discoveries is woven into the fabric of modern life. As we continue to explore the universe at its grandest and smallest scales, the discoveries of the proton and neutron serve as a testament to the power of human curiosity and our relentless pursuit of knowledge.